Okay, so EH equals Cm delta T is when there is a change in temperature. Today we're going to talk about when there's a change in state. Okay. So change in state, we have to use different equations. So we're going to talk about changes in state first of all, and then we're going to come across another equation that we're going to use. There's also EH. Okay, so we need to know the difference between the two. So first of all, heat energy and changes of state. So we're going to look a little bit later at how a refrigerator works. Okay, because it's not as straightforward as it might seem. So it has a motor that comes on from time to time. It has black fins and pipes at the back that get warm, and there are also tubes inside the fridge that get cold. Okay, so at home you can have a look at your fridge and see if you can see what happens. So we're going to talk about why that happens. So first of all, I've got a couple of little demonstrations I want to show you. So acetone is, if anyone ever wears nail varnish remover is made out of that kind of acetone. Okay, so it's kind of like a liquid. It evaporates very, very quickly. Okay, so if you ever drop nail varnish remover on your hand, it feels cold. I know not everybody might have experienced this, but it gets very cold, but it also disappears very quickly because it evaporates very quickly when it touches your hands. Okay. So we're going to look at. We're not going to do it today because we can't, unfortunately, because of the current situation. But acetone, if you do drop it on, if you do have access to any nail varnish remover and you want to just have a little go, just drop a little bit on your hands. You'll see that acetone evaporates and your hand feels cold. Okay. Now I've got at the front under my visualizer three thermometers with cotton wool at the bottom of them. At the moment they've got nothing on them. Okay. I'm going to soak one of them in acetone, soak one of them in water, and then just leave one as just dry in the air. Okay. So let's have a look at that. Okay, so at the moment, that's not particularly clear, but there are three thermometers there, and they're all relatively similar temperatures. And I can tell you the top one is 21.2, the middle one is 20.9, and the bottom one is 20. That's 1 minute. You wasted my time. The bottom one is 21.1. So they're all around about 21, 20, 21. Okay. What I'm going to do is the top one I will soak in acetone. Which is that one. It smells like nail varnish remover. The middle one I'll put in water. And the bottom one I'll just leave in the air. Okay. Sorry you can't see it very clearly. You can just about see it, but the top one is now 20.2. The middle one is I've gone up a little bit because it's room temperature water, but it's going down slightly, and the bottom one hasn't changed at all. Okay, so what we'll do is we'll just leave it there for a little bit. The bottom one's definitely gone down a lot. The bottom one's at 20 degrees, middle one 21.5.3, the bottom one 21.2. The top one's 19.8 now. Can you see those at all? You can just about see them. See for there. Oh, there we go. Yeah, sort of. So the top one, which is acetone, is the coldest at the moment. Then we've got water, which is the next coldest. And then we've got room temperature, which hasn't changed, 21.2. Okay, so you can see that top one's dropping very, very rapidly. Okay, and that's because the acetone is evaporating. It's using the warmth of the air to evaporate. Okay, so it's taking in heat energy from the air. So it's removing heat energy from the air, which is making the surroundings colder. So because it wants to evaporate, okay, to help it evaporate. See, that top one's all the way down to 18.2 now. The middle one's 20.3. The bottom one is 21.3. So that will stay the same, about 21. Still going down. Okay, so it's the thing that evaporates more rapidly. The quickest one to evaporate is one that's taking in heat from the surroundings and making the surroundings colder. Okay, and it's taking that heat to evaporate, to break bonds. So those chemists will know about when you evaporate, when you've got a liquid going into a gas, breaking bonds so it can move around. They can move around. Particles can move around more. Yeah. So 17. Yeah. So still going down. So I think that one's pretty much been the point. Coldest. Next cold, but not really changed much because the water's room temperature. And then that one's 22.1. So that's gone up a little bit, but that's probably because the room temperature's gone up a bit. Okay, so going back to my notes. The evaporating liquid causes a drop in temperature. And the faster the liquid evaporates, the bigger the temperature drop. So the water will be evaporating, but it'll be evaporating a lot slower than the acetone. The acetone evaporates very, very quickly. Yes. So for a liquid to evaporate, it requires to take in heat energy, guys, from its surroundings. So the quicker it evaporates, the more heat energy it takes in. So that's why it gets colder. Therefore, when a gas condenses, so it goes the opposite way into a liquid, it gives out heat energy. Okay, so when something's evaporating, when it's going from a liquid to a gas, it takes in heat energy, so it makes the surroundings colder. But when it's going the opposite way, so a gas to a liquid, it actually gives out heat energy, so it makes the surroundings warmer. Okay. So we're going to apply this knowledge now to how a fridge works, how a refrigerator works. Okay. So a fridge is, if you ever go behind a fridge and you go and touch the pipes, well, I wouldn't advise touching them, but if you go near them, they are warm. Okay. So a refrigerator keeps its contents cool by changing the state of a fluid called freon. Freon has a very high, what we call latent heat of vaporization. So it takes a lot of energy to turn it from a liquid into a gas. Okay, so it takes heat energy from the surroundings to go from a liquid to a gas and a lot of heat energy away. Freon also has a boiling point close to room temperature. The freon is pumped through the pipes in a refrigerator. When it reaches the freezer compartment, the freon expands rapidly from a liquid to a gas through a small valve. When it does that, takes in heat energy, makes the surroundings colder. The latent heat of vaporization needed to turn the liquid into a gas is taken from its surroundings, the freezer compartment, which becomes very cold. The pump takes the freon gas and compresses it into the thin black pipes at the back of the refrigerator. The freon then turns back into a liquid and releases its heat, its latent heat. And the heat is radiated away from the pipes into the room. So the pipes at the back are warm, because that's where it changes back into a liquid and gets warmer. But the inside the fridge is where it takes heat energy away from the surroundings so it gets colder. So let's look at this diagram here. So we're going to label each part. My printing missed off a little bit. Is your printing complete? Have you got boxes at the bottom? Okay. Right, so what happens is I'm going to start from the top. Okay, so at the very top box there, this is where the liquid evaporates into a gas. Okay, so it takes in a lot of the heat energy from the surroundings and it cools down. That narrow hole. Okay. Okay, so that's where it gets colder. Okay, and then inside the fridge, we've got this cold gas moving around. when that box shouldn't be there, I don't think that should be there. When it goes through that little sort of circular thing, that's called a compressor pump. So what it does is it compresses it, so it changes that gas back into a liquid, which gives out heat energy. So that really should be there. No. But you need to just know the theory behind when something changes into a gas, it takes in heat energy, so it makes it cooler. When something changes from a gas to a liquid, it gives out heat energy, so it makes its surroundings warmer. Yeah, basically. And this one should be here. That is liquid under pressure. So the liquid under pressure is outside, then it goes through that narrow hole and it evaporates, so it takes in heat energy here. Cools the surroundings. So here it's evaporating, so it's cooling the surroundings down because it's taking in heat energy. Cold around here, and here is when it condenses, so it gives out heat energy. So it's warmer outside, this is inside. Warmer outside there, inside it's cooler. Yeah, apologies, I don't know what happened to the printing there. Cool. Have a think while I leave that up, because I think a few people are still writing. Have a think about the example on the next page. I think it just needs more time to, but I'm not 100% sure. I'll find that out for you. Right, okay. Is everybody written that down? Okay. Right, so example 1. Sweating is a very important process because after perspiration forms on the skin, it evaporates to help prevent overheating. Where does the energy to evaporate the perspiration come from? So you've done a run. Sorry? Oh, I suppose originally it does, but where directly does it get that heat energy from to evaporate? Sorry? James, what did you say? Oh, you look like you were just saying something. Yeah, your body, yeah. So you've gone for a really long cross-country run, something like that, and you just stopped running, you're really warm, aren't you? So you start sweating, and the sweat evaporates from your warm body. So your heat in the surroundings or your skin. You're right, originally that does come from food, because you eat food and then it in. Okay. What kind of energy is required to make perspiration evaporate? I suppose we've already just answered that in the first part A, heat energy. And part C. Athletes among us might know this one. Why do athletes put on tracksuits immediately after an event? Jamie? Yeah. So to stop you losing the heat too quickly, yeah, keep your muscles warm. Oh, they do. Quite often, like sometimes, like after marathon runners, they put those sort of tinfoil things over people, don't they? And it's just if you lose heat too quickly, you get muscle cramps and things like that. I mean, I'm not an athlete, but I think that's how it works. Okay. Then example 2. Again, mine is cut off, but there's not really much more to it. It's kind of a plate there with some water. The picture shows a simple device for keeping a milk bottle cool. Okay, so what happens here? Well, we've got water here. Remember, if something evaporates, it takes in heat from the surroundings and it keeps the surroundings cool. Okay? You gonna answer that, Isa? Yeah, go for it. Yeah, exactly. So the porous material absorbs the water evaporates, making the surroundings cold. So the material around the milk bottle cold. I'll have some if they come. Wasn't myself, but if anyone needs the mirror, man. Right. Okay. Okay. Just doing some cleaning. Right. So the porous material absorbs the water. It's like a sponge. It takes in water. Yeah. The water evaporates, keeping the surroundings cool. Porous, yeah. Porous. Goes the back. Have you written this down? Okay, so when something evaporates, it takes in heat from the surroundings, making the surroundings colder. Okay, when something condenses, it gives out heat and it makes the surroundings warmer. Okay, same thing happens with other changes of states. So if you go from a solid to a liquid, it takes in heat from the surroundings. Because if you go from a solid to a liquid, or a liquid to a gas, Ava, then you're going from a less excited state to a more excited state. So solids are quite, they're happy, they don't move very much. Liquids move a little bit more, gases move more. So when you go from a less excited state to a more excited state, you need more energy to become more excited. So you have to take in energy from the surroundings. If you're going the opposite way, so if you're going from a more excited state to a less excited state, you don't need as much energy, so you give it out. Okay? And then you make the surroundings warmer. Okay? So cooling curves are curves that you would plot if you were watching something cool and you were taking the temperature of it. Okay, normally you would think, when we've done experiments like this in the past, you've just said, oh, the temperature just decreases as it cools down. But it does something a little bit stranger than that. So if you had a cooling curve for anything, this is any kind of substance, and this was your time, and this is your temperature, you would see something odd happening in the middle of it. So you'd see it, as you would expect, decreasing in temperature, but then it would level off a little bit. Oops. Helps if I change the pen. And then continuing to decrease. Okay? So what's happening here? What we have, so we'll say this is a liquid. Okay, it's starting off as liquid, changing into a solid. So what happens? Finlay, one more interruption from you and you can stay behind. So this part here would just be a liquid cooling. What do you think might be happening when it starts leveling out? Any guesses? Yeah? Yeah, that's where it's turning into solids. Okay, so freezing or solidifying. It's just this pen sometimes draws random lines. And then when it starts decreasing again, we've got a solid that's just cooling down. It would just continue down. So this line here, this leveling out line, is at the melting point. And you quite often see these types of graphs in multiple choice questions, and they ask you, oh, at which point is it a liquid, or at which point is it a solid, kind of thing. So you've got a decrease in temperature when it's just cooling down. Then you've got this leveling off part of the graph where it's changing state, and then it goes back down again when it's cooling down again. So the changing state, the reason it doesn't continue decreasing in temperature is because it's using the heat energy to change state. Okay. So let's fill in the gaps below this. So as the wax cools, it loses heat energy. As it is initially much hotter than its surroundings, it loses heat and its temperature falls. When the liquid wax reaches its melting point, it starts to turn into solid wax. It continues to lose heat as it's still hotter than its surroundings. There's two words that I've said so far, Finlay. Melting and solid. However, its temperature does not change. The heat it loses is due to the wax changing state from a liquid to a solid. Once the wax is all solid, it continues to lose heat and its temperature then continues to fall. Now, the energy a substance gains or loses when it changes state is called the latent heat. Okay, so that's quite an important term there. The heat gained when a substance changes from a solid to liquid, or loses when it changes from a liquid to solid, at its melting point is called the latent heat of fusion. So, solid to liquid, liquid to solid, latent heat of fusion. These are important because you will need to be able to use these in questions in the future. And the heat gained when a substance changes from liquid to gas, or loses when it changes from gas to a liquid, and its boiling point is called the latent heat of vaporization. Okay, so solid to liquid, it's fusion. Liquid to gas or gas to liquid is vaporization. Sublimation is when it goes from one end to the other end. without the in-between bit. So this happens when something melts or freezes. This happens, or this is used when something evaporates or condenses. So the tricky part here is when we do questions involving this, you have to pick out the correct number. These two things are different numbers. So it might be you're looking at water evaporating. So you have to look at the latent heat of vaporization. But it might be that you're looking at water freezing, and then you have to use the latent heat of fusion. Okay, so they're two completely different, well, they're not completely different things, but they are different numbers. So you have to be able to pick out the correct one. So it's important that you remember that fusion is when something goes from a solid to a liquid or a liquid to a solid. And vaporization is when something goes from a liquid to a gas or a gas to a liquid. Okay? So we're going to go through an example of this on the next page. Have a read through the next page. I'll just leave that out for a second. A couple of people still writing. Okay? So, specific latent heat. So the heat needed to change the state of a substance depends on two factors. The mass of the substance and the type of substance it is. So what it is. So water, paraffin, ice, yeah. Lots of different, three things that popped into my head there. So the equation for this is EH equals ml. So EH is the energy, the heat energy. And that's in joules, of course. M is the mass, which is in kilograms. And L is the specific latent heat. Okay. And the units for that is joules per kilogram. So it's a little bit easier than specific heat capacity, which is joules per kilogram per degree C. And the specific latent heat, L, is a measure of the amount of energy needed to change the state of 1 kilogram of a substance. And again, another reminder, because it is important, when the state changes from solid to liquid or liquid to solid, the specific latent heat of fusion must be used. And when it goes from liquid to gas or gas to liquid, the specific latent heat of vaporization must be used. Okay? So what do we use if it goes from water to ice? Thank you. There we go, one person. What do we use if it goes from water to water vapor? Yes. Okay. So just be careful. What do we use if it goes from solid ice cream to liquid ice cream? Fusion. Yeah. Okay, good. Right. So example 1. The specific latent heat of fusion of ice is 3.34 times 10 to the 5 joules per kilogram. Calculate how much energy is needed to melt an ice cube of mass 10 grams. So it's just melting. So we're just going to use EH equals ml. Sometimes you might end up with something that's melting then increasing in temperature. So that's where you're going to have to use two equations separately. But this one will just it's just an ice cube melting. So the mass is 10 grams. So remember, I need to put that into kilograms. So 0.01 kilograms times by, well, luckily we're just given one latent heat of fusion. That's okay. We know we're using the fusion. Sometimes the question might give you more than one number and you've got to pick the correct one. But in this case, we're just using the one that's given to us. So 3.34 times 10 to the 5. And that should come to 3,340 joules. And example 2. The specific latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. So L, and L, I'm going to put V for vaporization, is 2.26 times 10 to the 6 joules per kilogram. 6 times 10 to the 5 joules of energy are supplied to the water. So the energy is 6 times 10 to the 5 joules. Which is not really boiling, so we're not increasing in temperature, it's just boiling by a kettle element. To calculate how much water is turned into water vapour, so we want to know the mass of water. So EH equals ML. So which one? LV? Oh, 5. So 6 times 10 to the 5 equals the mass times by 2.26 times 10 to the 6. So the mass will be 6 times 10 to the 5 divided by 2.26 times 10 to the 6. And that should come to 0.265 kilograms. You can change it into grams if you want to, but you don't need to. Alright? What test? No. We have a test at the end of every booklet. We're nowhere near the end of the booklet. Okay, right. So the next page is a little demonstration experiment that I've got set up at the end of the desk. So what we're going to do is we're going to try and work out the specific latent heat of vaporization of water using a kettle and a balance. Okay, so I've got a kettle and a balance up there. I made my cup of tea earlier, so still got water in it. So to calculate the specific latent heat of vaporization, we have to measure the amount of energy supplied to boiling water and measure the mass lost, so the mass of liquid that is changed into water vapor. Okay, so this can be done by boiling a kettle, and then rather than letting it automatically switch off, letting it continue boiling. So basically what I do is I just keep flicking the switch back on again, and it'll keep on boiling, and some of the water will evaporate. Okay, so the mass will change. To find out the energy of the kettle, obviously we don't have it hooked up to an energy meter, but we can use energy as power times time. I do know the power of my kettle is 2,000 watts. And I'm just going to go for 60 seconds. Okay, so a minute. So what I'm going to do is I'm going to measure the initial mass and the final mass, and then we can work out the mass loss just by finding the difference between the two. And then what we do is we know that energy is power times time, which is also equal to mass times the latent heat of vaporization. So the latent heat of vaporization is power times time divided by that mass lost, okay, in kilograms. So what we're going to do is I'm going to find out what the mass lost is. Well, I'm going to find out what the initial mass is and the final mass. And then you guys are going to calculate the latent heat of vaporization. Bearing in mind that the actual value is 2.26 times 10 to the 6 joules per kilogram. So we'll see if we can get anywhere close to that. So first of all, the initial mass So how about you do that? Right. So I'm waiting until it starts running and then I'll start my timer. We drink tea in the physics department. So I'll just wait till that boils. Right, okay, it's just about boiling now. So I'm going to just turn my stop clock on and just heat it on pressing my button so it's not boiling. Right, okay, so final mass, guys, is 2,274.3. Okay, so 2,274.3. Well, you need to get your calculator out and work out. Right, so work out the mass loss in kilograms and then put it into this equation. So 2,000 times by 60 divided by the mass loss in kilograms. Put it in again. So, is that not right? Is that right? 20,000. Yeah, so you take that with that. Yeah. Yeah. So 3.1. No, no, that's the point. That's the point. Okay. Right. So you should be getting, James, what did you get for the answer? I'll do it then, instead of messing around. What did you get, Beth? You don't have an answer, do you? Sorry, you got what, sorry, Jamie? Alright, and what did you get for that? Alright, that's good. Yes, it's not too bad. Not too far off. Okay. Finley, sit down properly. Face the front. Okay, so I got 3.09 times 10 to the 6 joules per kilogram, which not actually is not that far off. I've done much worse before. So the actual value should be 2.26 times 10 to the 6, so we're in the right ballpark area. Okay, so on the page, there's space for evaluation. Ava, what could have gone wrong in this? What could we do to improve, or what could have caused any errors? Sorry? Talk about like the experiment itself. Yeah, heat energy could have been lost to the surroundings. Yes, so yeah. So as Ava said, what's the special word that we would use to stop that happening? Insulation. Yes. Can anyone think what else might have gone wrong? Why didn't we get like the exact value? You know? Yeah, exactly. The kettle wasn't working at its top efficiency. Those are the two main points. Can anyone think of anything else that might have gone wrong? You get a better kettle. Use better equipment. Yeah, I could have, stopped the stop clock wrong. No, I think I was all right, but you never know. Timing could have been off. There's not really anything you can do to improve human error. Robot. No, you want it to be starting out boiling because all you want is just it keep on boiling. Is that math? The scale could have been scale could be inaccurate. Yeah, guys, listen. Asa said the scale could have been inaccurate, which is absolutely fine, it could have been. The batteries might have been out of charge yet or running low.